Assalamualaikum and good day everyone. My name is Norazirah Binti Razi and my title for final year project is Tackling COVID-19, the search of potential inhibitors for Papain-Like protease of novel coronavirus using molecular docking approach. A continuous outbreak of coronavirus-associated pneumonia, severe acute respiratory syndrome coronavirus 2 or SARS-CoV-2 was identified in Wuhan, China in December 2019. Infection spread throughout China and the other nations all over the globe throughout the coming weeks. On 12 February 2020, World Health Organization WHO referred the disease as COVID-19. Structurally, SARS-CoV-2 contains four major structural proteins comprising spike glycoprotein, small envelope glycoprotein, membrane glycoprotein, and nucleocapsid protein, as well as numerous protein accessories. Drug repositioning has served as a technique embraced by many researchers to find successful treatment within a limited period. In addition, simulated molecular docking screening is emerging as an effective method for finding new antiviral molecules, where researchers could use this tool as corresponding method to ensure that the production of different compounds or the relocation of drugs can be allocated. The protein and ligands used in this molecular docking is papain-like protease, prosinamide, levamisole, and diclofenac. As for the problem statement, World Health Organization has declared COVID-19 a worldwide emergency and virulent disease. Induced by the SARS-CoV-2 virus, it may cause symptoms such as fever, cough, pneumonia, nausea, including tiredness. To inhibit or treat human coronavirus infection, there is still no antiviral drugs. Drugs that target this protein and several steps of viral replication are currently ongoing. The objective of this study is to identify potential drug candidates for the treatment of COVID-19 by investigating the binding mechanism and molecular interactions between prosinamide, levamisole, diclofenac, and papain-like protease of novel coronavirus using molecular docking simulation approach. To meet the objective of this study, the following scopes need to be considered. The scope determines the extent of investigation in achieving the objective of the study. First, the COVID-19 receptor used in this study was papain-like protease, and the drugs were selected randomly based on previous literature review. The complexes of papain-like protease and drugs were obtained from molecular docking methods. Next, the selection of the best 10 complexes were based on the lowest energy conformation. And the last one is the binding modes between potential drugs and the receptor will be investigated by looking at the molecular interaction such as hydrogen bonding, hydrophobic interaction, and electrostatic interaction. Here are the steps for molecular docking. First, select protein target and ligand molecule. Second, the receptor was retrieved from protein databank and the ligands was retrieved from PubChem websites. Third, perform receptor and ligand preparation using Autodoc tool software. Fourth, the binding site identification using BioVia Discovery Studio software. Fifth, preparing grid box for protein ligand binding site. Sixth, conduct protein ligand docking using Autodoc Bina software. And the last one is analysis of protein ligand docking using LeakProt Plus software. For the receptor preparation, the papain-like protease of SARS-CoV-2 was retrieved from the protein databank. Using Autodoc tool software, water molecules were eliminated from the protein. The initial directory was set to the desired folder before docking. The processed protein molecule was imported into the Autodoc tools. The polar atoms of hydrogen were added for the protein. The Coleman charges were computed. The protein was then saved in the format PDBQT, which was then used as the target. And for the ligand preparation, prosinamide, levamisole, and diclofenac were retrieved from the PubChem database. The ligands were converted using PyMol software to protein databank format and used for docking, and they were imported and saved in PDBQT format into Autodoc tools. Next, before proceeding to molecular docking, there are another step which was to identify the binding site of a protein. In docking, grid box coordinate X, Y, and Z must be specified in the config file. It is important to know what the coordinate of the grid box is because this is where the docking simulation take place to find the best pose for docking to occur. For the preparation of grid, the critical step in molecular docking is to assign the grid parameters as it navigates the ligand to the protease binding site. The spacing of the grid was set at 0.375. The value of the center grid box was set as the following. The output has been saved to the file format of the text documents. The config file was created and saved in the file format of text document. The molecular docking simulation on all the input file was performed using Auto.vina, which was called using the C command prompt. After the simulation complete, the log and output files were produced. Figure below is the screenshot of the log file. For the last step of this molecular docking simulation is analysis, which is done after the completion of the docking between the protein and the ligand. The analysis was carried out using the program LeapFrog+. The aim of this analysis was to identify the number of hydrogen bonding, hydrophobic interaction, and also the binding energy. Molecular docking between papain-like protease and three ligands, which are prosanamide, levamisole, and ticlopidine, has been done to identify if this chosen drug will be a potential drug to inhibit COVID-19. In this context, there were 20 binding sites set, and the best binding site is based on the lowest binding energy. The first 5 of complexes were chosen based on the lowest binding energy for each of the ligands. This figure shows the first, second, third, fourth, and fifth complexes as the result from docking between papain-like protease and prosanamide. The table below shows the analysis of 5 first complex that has been chosen from 20 complex between the protein papain-like protease and prosanamide. The first complex has 0 hydrogen bonding, 11 hydrophobic interaction, and has the lowest binding energy, which is negative 6.0 kcal per mole. For the second and third complexes, they have the same binding energy, which is negative 5.9 kcal per mole, but different hydrogen bonding and hydrophobic interaction. The second complex have 4 hydrogen bonding and 10 hydrophobic interaction, while the third complex have 1 hydrogen bonding and 9 hydrophobic interaction. While for the fourth and fifth complexes share the same number of hydrophobic interaction and binding energy, which is 7 and negative 5.8 kcal per mole respectively. They do not have the same hydrogen bonding, where the fourth complex has 2 hydrogen bonding and the fifth complex has 4 hydrogen bonding. This following figure shows the first, second, third, fourth, and fifth complex as the result from docking between papain-like protease and levamisole. Based on the table below, which shows the first and second complex have same number of the hydrogen bond, which is 1, but for hydrophobic interactions and binding energy, the first complex has 8 and negative 6.2 kcal per mole, and for second complex have 7 and negative 6.1 kcal per mole respectively. For the third and fifth complexes, both have no hydrogen bonding and 7 hydrophobic interaction each, but it has different binding energy, where negative 6.0 kcal per mole for third complex and negative 5.9 kcal per mole for fifth complex. As for the fourth complex, it has 1 hydrogen bonding, 5 hydrophobic interaction, and negative 6.0 kcal per mole for binding energy. The following shows first, second, third, fourth, and fifth complexes as the result from docking between papain-like protease and ticlopidine. Table shows that all 5 complexes have no hydrogen bonding. The first and third complexes has 9 hydrophobic interaction, but has negative 7.0 kcal per mole and negative 6.5 kcal per mole binding energy, respectively. The hydrophobic interaction and binding energy for the second complex is 8 and negative 6.7 kcal per mole, while for the fourth complex it is 11 and negative 6.3 kcal per mole respectively. Finally, complex 5 has 7 hydrophobic interaction and negative 6.5 kcal per mole binding energy. As a conclusion, since they bind to the active site of the papain-like protease of SARS-CoV-2, the results of molecular docking of 3 distinct drugs with papain-like protease reveal that they might be potential anti-SARS-CoV-2. Based on the result obtained from molecular docking among the 3 drugs, which are prosanamide, levamisole, and ticlopidine, ticlopidine is the best in comparison to levamisole and prosanamide. This is because ticopridine has the lowest binding energy of -7.0 kcal per mole, while prosanamide and levamisole have -6.0 kcal per mole and -6.2 kcal per mole respectively. Ticopridine also has 9 hydrophobic interaction and 0 hydrogen bonding. For future recommendation, more ligands should be tested to bind with papain-like protease by using molecular docking, and the dark protein and ligand should undergo virtual screening and be analyzed through experiment. That's all from me. Thank you.